I'm Professor Rad, and this is Precalc video 2.2, the factor theorem. In this video, we'll be continuing our conversation about polynomials, and we're actually going to look at two theorems that will help us achieve one of our overriding goals for this unit on polynomials. So here's what that goal is. Our goal is to be able to solve equations of the form polynomial equals 0. That's what we want to solve. If the polynomial is in standard form, meaning all the terms are written out and it's expanded, then this can be a difficult equation to solve, especially if the degree of the polynomial is larger than 2. So we can solve linear equations. We're pretty good at solving quadratics, but what if we have a cubic or a quartic or a degree 700? Oh gosh, how can we solve those formulas? How can we solve those equations? So in math, you have a lot of different, statements that you use. Some of them are called axioms or propositions. Some are called theorems or lemmas. So essentially, like an axiom is something that is like so obviously true that you can just state it and it's like, that's it, it's done. A theorem is something that you have to prove, that you have to show through deductive reasoning, or sometimes inductive reasoning, show that you can draw this conclusion. So in this class, we're going to be stating and applying theorems, but we won't always be proving them. In fact, we often won't. We're going to leave that for your calculus class or beyond. So we've already seen a theorem so far. We've seen the extreme value theorem, right? Where we had this statement of turning points or maxes and mins on a closed interval. So we're going to see a lot of theorems that relate to polynomials. So what we're going to tend to do in these videos is we'll state a theorem and then we will show an example of how that theorem is applied or used. So in your homework and things, it's going to say, use the theorem to answer this question. So some of our theorems will also be named. Those are the really important ones. And some of them will not be named. So in this video, we're going to do one named theorem and one theorem that doesn't get a name. So we'll do the named theorem first, and this is called the factor theorem. So I'm going to use THM as my abbreviation for theorem, and I'm going to number them because, as I mentioned, some of our theorems have names, some of them don't. So if I reference a theorem in the future, I'll be referencing it by its number. So our first theorem is the factor theorem, and it says, let f of x be a polynomial function. So this is like the condition of your theorem. This is the situation you have to be in. So the only component to our situation is we have a polynomial. If you have a polynomial, then x minus c is going to be a factor of that polynomial if and only if f of c is 0. So real quick, this IFF is not a typo. So this is a shorthand. You might also sometimes see it written as a double arrow like that. And it means if and only if. When you have an if and only if theorem, what that means is that if you have one side of the statement, you can conclude the other side. So for example, if I know that x minus 3, I'm just going to pick a number for c to make it easier to talk about. So if I have x minus 3 and that's a factor of my polynomial, that means that when I plug 3 into the function, I'm going to get 0. Similarly, if I know like f of 7 is 0, then that means that x minus 7 is going to be a factor. So let's do an example of applying the factor theorem. This example says to use the factor theorem to show that x minus 2 is a factor of this polynomial f of x. Then we're going to factor this function completely. So the first step is to use the factor theorem to show that x minus 2 is a factor. So x minus 2 is going to be a factor. This is our x minus c. Okay, so it's a factor if f of c, or in this case, f of 2, is going to equal 0. So that's what we're going to do first. So we need to find f of 2, and we want to see, does that equal 0? So let's substitute in 2 and find out. So f of 2 is going to be 4 times 2 to the 4th minus 15 times 2 squared minus 4. So 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. And 2 squared is 4. So then 4 times 16 is 64. This will be 60. And then 64 minus 60 is 4, minus 4 is 0. Very good. By the way, you know you get it correct when you find Harry Potter. There he is with his little lightning bolt scar. Okay, so we found that f of 2 was actually equal to 0. So therefore, by the factor theorem, x minus 2 is a factor of f of x. And again, we know this, it's a factor because f of c, or in this case, f of 2, was equal to 0. Now, the next part of this problem says to factor f completely. So when we go to factor a polynomial, think back to what it means to like factor a number. So if I have a number like, I don't know, 24, and I want to factor that, I might say, oh, I know that 2 goes into 24. So I can split that up into 2 times 12. And then, oh, now I can break down 12, split that up into 2 times 6. And 6 is going to break down into 2 times 3. So I end up with 2 times 2 times 2, or 2 cubed, times 3. So when we go to factor a polynomial, we're going to be doing the same process, except now instead of numbers, we have polynomials. So we're going to start out with our polynomial, and we want to see, can we find one factor to break it down by? Because once you break it down one factor, the subsequent polynomials are going to be easier and easier to break apart. And then in the end, every factor we found, we're going to multiply together to get our final polynomial, to get our factorization. So what the factor theorem allows us to do is it gives us a place to start. It gives us something to begin to break down by. Now, there are a variety of techniques that you can use to factor polynomials. In this video, I'm going to use a method called synthetic division, and then we'll visit some other techniques in the future. So synthetic division works really, really well if you are dividing by a linear polynomial. So if we're dividing by x minus 2, then synthetic division is going to be a good technique for us to use. The way that we're going to set this up is I'm going to create kind of like a little box here. And I'm going to put the coefficients of this polynomial, f of x, inside the box. Now, I want to make sure that I include all of the coefficients. So if a term isn't present, I have to put a 0 there to represent it. So we have 4x to the 4th. So I'm going to put a 4 here. There's no x cubed term. So this is where I'm going to put in a 0 for the x cubed term. Negative 15 for the squared term. 0 for the linear term. And then negative 4 at the end. Then what I'm going to be dividing by is this factor of x minus 2. So I'm going to put like the c outside. I mean, the c should be outside. If you have a c inside, then that's probably a problem. There's been some flooding, but in this case, we're going to put the 2 on the outside of our brackets here. And what we're going to do is we're going to skip a line and draw a line underneath. And you bring first term down. And now we're going to do a series of multiplications and addings to continue our synthetic division. So now I'm going to do 2 times 4. That's going to give me 8. I'm going to put the 8 here. Then I add down. So 0 plus 8 is 8. And we're just going to repeat this process. 2 times 8 is 16. And then I'm going to add negative 15 plus 16 is 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 4 and 4 is 0. This is our process here. And I'm going to cut off this last piece of 0. What this means with our synthetic division is that the 0 is the remainder, and that's what we want because we know that x minus 2 divides this polynomial perfectly. So we end up with a remainder of 0. And when we factor that out, we end up with a polynomial that has these coefficients. Now, if you have trouble figuring out what the power of that polynomial is going to be, I count from here 0, 1, 2, 3. So this is going to be 4x cubed plus 8x squared plus 1x plus 2. And what we've done, we've just factored out that x minus 2. And if you were to distribute the x and the -2 to each of these terms and combine them, you should end up with this guy back up here. Now we're going to continue with any other factoring techniques that we know. So for example, I could repeat this process and see, okay, is x minus 1 going to be a factor of this new polynomial? Kind of break it down, see what I get. But at this point, we would kind of be guessing wildly because we don't have any idea how to find a good number to plug in. It's for a future video, we'll do that eventually. So for right now, let's use factoring by grouping. That's going to work well for this polynomial. So when I look at this polynomial that's left here, I notice that these first two terms have a common factor of 4x squared. So I'm going to factor that out of these two terms. And that's going to leave me with an x plus 2. Okay? 4x squared times x will give me back this 4x cubed. And 4x squared times 2 will give me this 8x squared. And then I'm going to bring down this x plus 2, but I want them to be grouped together. So I'm going to write that as 1 times x plus 2. Now, factoring by grouping only works if these two, I call these blobs, if these two blobs are the same. So in this case, they are. So we can factor the x plus 2 out of these two bigger terms. And then that will leave us with 4x squared plus 1. And then I'm going to bring down my x minus 2. And there we go. Okay, and then we can continue to factor. So we've got our term of x minus 2. We've got our factor of x minus 2. We've got our factor of x plus 2. And now we want to see if we can break down 4x squared plus 1. So if I'm living in the land of real numbers, this does not factor anymore. Let's use what we know about quadratics to help us understand why. So I know that this is going to be a smiling parabola because the coefficient of the x squared term is a positive, so it's going to be smiling. And we have plus 1, and we don't have x minus anything. So that means the vertex of this parabola is at 0, 1. So our vertex is at 0, 1, and we are smiling. So this means this parabola never crosses the x-intercept, which means it doesn't have any real roots. It doesn't have any real x-intercepts. So that means it's not going to factor down anymore over the reals. So this is going to be our completely factored polynomial. For now, maybe in the future, we'll expand our world a little bit. So we're not looking just at reals. Maybe we'll look at, say, some more complex values. But for now, this is where we're going to stop. Okay, so I promised you 2 theorems in this video. So let's look at the second theorem, which doesn't have a name. So we'll just call it theorem 2. Theorem 2 is a type of theorem called the following are equivalent type of theorems. What this theorem means, or what that idea means, is that you have a list of statements, and if you know one of them, you automatically know all the others. So when statements are equivalent in math, it means that if one is true, the other one's going to be true, and vice versa. So for this theorem, we have 4 statements about a polynomial, so that if we know one thing about a polynomial function, then we know the other 3 things. So if I know that, for example, r is a real root of this polynomial function, then we know that r0 is an x-intercept. We know that r is a solution to the equation f of x equals 0, which remember, that's our goal. We're trying to solve equations of the form polynomial equals 0. So another way of phrasing this statement is that f of r will equal 0. And we know that x minus r is a factor of f of x. So the factor theorem is hiding out in this theorem in these last two statements. Remember that x minus, now I'm using r instead of c, but doesn't matter what letter I use. So x minus c is a factor when we have f of c equal to 0, right? So that's the factor theorem hiding out. But now we're kind of expanding that concept a little bit to include these other statements as well. So if you want to take a moment and jot this down, feel free to pause the video here and do so. And then we'll do an example. So let's do an example of applying this theorem. A way we might see this in our class is like, let's say suppose I know that f of -3 equals 0. What else can I conclude? So what else do I know? So in this example, I know that f of -3 is 0. So I know something of this form, f of a number equaling 0. So I know line 3. So now I'm going to apply that to the other three statements. So first, this means that I know that -3 is, because this is f of r, so r is our -3, is a real root of f. I know that -3, 0 is an x-intercept. And for number 4, well, I got to be careful here because r is -3. I have x minus -3. So that means that x plus 3 is a factor of f. So for right now, while we're learning this theorem and making sure we know like what it means, you might be asked, you know one thing, what else do you know? So you'll be expected to identify those and apply the value of r for those three other statements. In practice, once this theorem becomes like a part of your heart and mind and soul, then you'll just be able to jump from one of these to the other. So I'm in a place in my life where I'm like, if I hear an x-intercept, of course that's going to mean I have a root. And of course that means I have a factor, and I'm going to have a solution to y equals 0. So at some point, this will become something where it's like, you don't need to reference it. You can just kind of draw those conclusions because we'll be using those conclusions so very often. All right, and that's going to wrap up our factor theorem video. You might have been wondering, in that previous example we did, and I said show that x minus 2 is going to be a factor of this polynomial. And where did x minus 2 come from? Right? So in our next video, we're going to find out how we can figure out some good candidates to test to see if they're going to be factors of our polynomial, so that we're not just like left with all real numbers in the universe trying to figure out, okay, is this a factor of the polynomial? Is this one? Is this one? We're going to find a way to at least narrow it down from infinity to something finite. So I'm looking forward to seeing you in that video. In the meantime, I hope this was helpful in understanding the factor theorem, and I will see you in the next one. Bye for now.